So, welcome to module 9.4, and in this module we will be talking about the parsing, which is given a grammar and given an input, whether that input actually adheres to that grammar, and that is what we will be doing as a part of this module. So, what we did in the previous module, we actually basically constructed a tree. A tree is nothing but a hierarchy. So, you know, family tree, like that. So, like this is an hierarchy, right. For example, the dog ate my homework, for example. Let us take an interesting example. Now, is this grammatically correct? That means using these rules of the grammar, can I basically arrive at this sentence, right. So is this sentence adhering to my grammar? How will I prove that? Yes, we start with a sentence here, right. The sentence has a noun phrase and a verb phrase. The noun phrase has a determiner and a noun. The verb phrase has a verb and a noun phrase, right. So, the determiner is the noun is dog, the verb is ate, the noun phrase again has a determiner and a noun, and determiner is my, and homework, noun is homework. So, from the rules of the grammar, I am able to derive that the dog ate my homework is indeed a sentence, because the dog ate my homework has a noun phrase followed by a verb phrase. The noun phrase is the dog. Why is the noun phrase the dog? Because noun phrase can have an optional determiner and a noun, and that optional determiner is the and dog, and hence the dog is a noun phrase. And similarly, ate my homework is a verb phrase, because the verb phrase can have a verb followed by a noun phrase, and the verb is, in my case, is ate, and the next noun phrase can have an optional determiner and noun, and the determiner in this case is my and homework. So, this my homework is a noun phrase, ate my homework is a verb followed by a noun phrase, which is a verb phrase, and so the dog noun phrase, ate my homework followed by ate my homework verb phrase is indeed a sentence, and hence this particular sentence adheres to the grammar, it agrees with the grammar. So, this is grammatically correct as per the rules that I have given for this. So, what I have constructed here is I have parsed this. Parsed means I have looked at every part of this language, I have parsed this entire sentence, and I am proving that this sentence adheres to my grammar, and so I have essentially constructed what we call as a parse tree. So, this is a parse tree. Now, the same thing that we need to conduct construct for everything. For example, while count is less than 100, so this is the input that I am giving. While count is less than 100, let count equal to count plus 1 semicolon, right. Now, is this one statement, is this a correct statement? Yes. Yeah, a statement can have a while statement, if statement, or while statement, or let statement. So a statement can be a while statement as per this rule, first rule. Now, that while statement basically should start with a while, yes, then followed by a parenthesis, yes, then followed by an expression. That expression can have a term and another op and term, which is optional, I can use it. So, term, op, term. The op, so the term can be a variable name, so that is count. The op can be any of the symbols, so this is less, and the term can be again a constant. As per this rule, again the term can be a constant, and that constant can be a decimal number 100. So, this is an expression, count less than 100 is an expression. So, there is an expression after that. In the while statement, after this expression, now we are going to have a closed parenthesis, yes. After the closed parenthesis, you need open braces, yes, that is there. Then there should be statements. At the end of the statements, you need to have a closed parenthesis. Now, let count equal to count plus 1 semicolon should be a statements, yes. Yes, a statements can have one or more statement, and so in this case, let us say I will have one statement here, and that statement can be if statement, while statement or let statement. So I decide on its let statement. So statements has one statement. See here, I am moving the mouse here. Statements has one statement. Statements has one statement, and that statement has let statement. The let statement again should have a let followed by a variable name, that is count, then an equal to, then another expression. Expression essentially is can have a term, op and term, and that term is a variable name, is count. Another op can be plus, the next term can be a constant which is 1, and it should be followed by a, the let statement should be followed by a semicolon here. So that is a semicolon, okay, and then end parenthesis. So while parenthesis count less than 100, close parenthesis, open braces, let count equal to count plus 1 semicolon, close braces, adheres to this grammar. So this is correct, right. So what we are now doing is what we call as syntax analysis, where is there an error in the input in terms of adhering to a grammar. That is what we are trying to do, and this is what we have achieved here. So what we will be doing as a part of this parsing is that this is what we need. So the moment I get this while count less than 100, let count equal to count plus 1, so this entire statement should, whatever we have done here, this parse tree, right, so should come up here. So I will say, I will start off with while statement, then I need to have a keyword, while slash keyword, then I need to have symbol slash symbol, then I need to have an expression. So let us just take the first level view. While statement should have a keyword followed by a symbol followed by an expression, it ends here, then again followed by a symbol which is this thing, followed by another symbol which is opening of this parenthesis, followed by statements, the statements end here, then followed by a symbol which is this close parenthesis, and this is the end of while statement. So while parenthesis, close parenthesis, open braces, close braces is there. Now intermediately between these two parentheses I need expression, and then between these two braces I need statements. So that we need, that we saw here. So the expression essentially had a term followed by a symbol followed by a term, right, term op term, count less than 100, and similarly the statements had a statement which is a let statement for let count etc., and that let statement basically had a let is a keyword, then an identifier which is a count, then a symbol which is equal to, then another expression. The expression in turn had a term, a symbol and a term, and so on and so forth, right. So whatever we have generated as a parse tree here, we generated it as an XML file. This is called extended markup language. Very simple here, just we need to write this down. So from the tokens that we have generated as part of your first part of your module project 10, we need to now go ahead and generate this XML file or parser output, and that will make the whole thing. So what we need to now do is, from the token, how do we generate this XML file? That code we have to write. So what happened in the tokenizer? We gave, say, main.jack, it gave us main.tok token. That main.tok should be taken and it should give us as main.xml, and that is all about this project 10. So how do we go about doing this process? So this is what we have to write. So we can write it in this entire thing is, we will give you a very sneak preview of this, but then so for each of the, so we start with statement, right. So statement, basic statements has one or more statement. Statement is the start. So statements is the start. So So we have one or more statement, and so for each statement, so I'll have something called compile statements, and that compile statements will essentially have compile if statement, compile while statement, compile term, etc. For all these things I need a compilation, right. So I have different routines, one handling statements, one handling if statement, one handling while statement, like that, one handling term, etc. So the parsing process is like this: you follow the right hand side of the rule and parse the input accordingly. If the right hand side specifies a non-terminal, rule xxs, call compile xxs, and do this and keep doing this recursively. So let us see how this example. For example, I have while count less than 100, let count equal to count plus 1. So what would be the token for this? So I will have a keyword while to start with. So what you do? So let us assume that we read while. So we know that this is a keyword. So immediately we have to now go and call compile while statement, right? Right. So immediately I have to go and call compile while statement, because while is a keyword, and so we go and call compile while statement. And what will compile while statement do? This is what it will do. So compile while statement will first say, hey, I am in the XML file, it will say while statement, it will print while statement. So this is the output. So while statement, then immediately it will go and you have already seen a keyword while, so you go and print this keyword while. Then it has to see, it will go and check if the next element is a symbol and that symbol is a open parenthesis, right. It will check, and if it is true, then it will put it here. If it is not true, then it has to say parenthesis missing. When you do a syntax, when you do C, when you compile the C program, you say parenthesis is missing, right. So who tells this? This particular rule tells this. Then the next step is that it goes and sees, then next it has to see an expression. So immediately it will call compile expression, right. So what will compile? So immediately this will put expression here, and what will compile expression do? Compile expression essentially has to look for a term. So immediately compile expression will call compile term, because immediately it has to look for a term, and the term I don't need anything. Term I should check whether it is going to be an identifier or a integer constant, right. Term can be an identifier or a integer constant. So in this case it is an identifier. So I just put identifier, count identifier, and that's how your tokenization would have happened. Tokenization would have said keyword while keyword, symbol for this parenthesis, and count will be as a identifier. So it will see an identifier and it says count, right. Then it comes, it see an less than. So this term should now go and see if there is an op. If there is an op, no, it doesn't. So this one term is over, term var name is over. Then I go back, the compile expression now will see there is a symbol. It goes back there, and now it goes and sees, yes, there is a symbol. So it puts slash symbol there. Then now it sees, the moment it sees a symbol, now again it will as term. So again it will call compile term, and the term in this case we have to check whether it's a constant or this. Yes, there is an integer constant, and then slash term ends. Okay. So what has happened is I am moving from one token to another token. The first token I saw was a keyword while, so immediately I call compile while statement. The moment I call compile while statement, that compile while statement will start ensuring that your while is adhering to the syntax of what the while should be, right. So first there should be a keyword while, it did it. Then it says that there should be a parenthesis open, that also there. Then there should be an expression. Now, so the compile while statement will now call compile expression, right. And now the compile expression immediately will call compile term. It will, because there is one term, surely there should be a term. Now the term will now go and compile term will go and check whether it's a variable or a constant. So immediately it knows that it's an identifier, so it's a variable name. So identifier count, it will put there slash identifier and it will go back, right. So term is finished. Now again you will go back to compile expression, and then the compile expression will see what next. If it sees a symbol, right, then it outputs the symbol, and after that symbol it should see another term. So again it will call compile term. Now the compile term will check whether the next is it seeing a variable or a or a key variable or a constant. In this case it sees a constant, it finishes and returns. After that the compile expression will see is there anything more, nothing. So it can be only 2, so then it returns back. So it returns back to whom? Compile while statement. Now the compile while statement is at this point, right. Now the token, now it is C, it goes back to the compile while statement. So the expression is over. Now the while statement should now see a symbol which is close parenthesis. If it doesn't see that symbol close parenthesis in the token, next token, the next token is not a symbol, then again it should give an error, right. But in this case, yes, it sees a symbol. Now after that symbol, it should now see another symbol which is the opening of the braces, opening brace. Now after that it should see statements, right. Now immediately it will call compile statements. The compile statements, now immediately the moment I see a compile statements, then I will go and check whether compile statement will have 0 or many statements. So I will go and check if I have a let or while or if. So I see, yes, there is a let statement, so, right. So the moment I go to let statement, so I will have compile let statement. So I see a let, then I make compile let statement. So the moment I see compile let statement, now I have variable name let. So it should first see what should the let statement see? It should see a keyword let, then it should see the next token should be a identifier which is var name. It should see an identifier, right, because var name is an identifier. Yes, so it sees an identifier count. Then it should see an equal to, it's a symbol. Yes, it sees that. Then it should see an expression, right. So immediately it will again call compile expression. The compile expression immediately it will call compile term, and the term will see inside the term again you will see identifier. Compile term will return back. Again you will see term slash term, then you will see a symbol slash symbol, then you see another term which is in constant, and then you come back. So this is how the compile expression will complete it. Then you go back. After that for the let, so you go back to the let compile let statement, right. You are compiling this, and then you should see a symbol there. Then this let statement is over. Then we go back, the let statement is over. Now we go back to compile statements, and you actually don't see any more statements there. So you finish it. So this is how the while statement. Now so once the statements finish, then you come back to the while statement. Again you need to see the last symbol which is closing parenthesis, right. So this is how the parsing process basically. So you code these routines. So I will have something called compile while statement, compile expression, compile term, compile statements, compile let statement, etc. And each of these routines will check if the tokens that are following adheres to certain rules of this grammar, right. So you have to just code these 4 or 5 routines and then pass the token one by one, line by line. So every line had a token, right. So we have to pass the token one line by line to this thing, and every fellow will check whether things are working, the whole thing is correct, and then it will generate this entire output, right. So this would be the parser output that will be generated, right. So this is the entire parsing process. It's a very simple thing that we can write. Okay. Right. Right. So, a small introduction to finite state. So, you will be learning a course called Theory of Computing as a part of your thing, right? Or in your, it's so basically you will be discussing about automata theory, etc. As a part of your Theory of Computing course, you will be learning this grammar. Whatever I have taught so far is one very minor subset of a reasonably large subset of what you will be learning in a Theory of Computing course. Theory of Computing basically talks about languages and the grammar, computing languages and their associated grammar, and that is what we have covered now. Now, what we saw now is called a LL grammar, okay, which can be parsed by a recursive descent parser without backtracking. So, these are all big words. I will basically explain you I'll basically explain you what is this grammar and everything. See, what is backtracking and this thing, right? So in this case, let us go back to what we saw earlier here. When I was, let us go back here. When we start parsing this, we started initial, right? We started with the let us go back quickly. In the entire process of this parsing, right? Let us go there. The entire part of this parsing. So, we started, so while this input came, we started with while statement. From the while statement, we arrived at while, then we arrived at the symbol, then we called the expression and we finished off count less than 100, and then went. In this entire process, we did not revisit our decision, right? So, by looking at while, we are very clear that this is a while statement, this cannot be any other statement, it is a while statement. So, if at all I want to process this entire statement, it should adhere only to the while rule, there is no other rule that will fit into it, right. So, the first thing, the moment I saw while, I said I will start using this while statement rule to prove that this statement essentially belongs to this grammar, right, and I had no doubt about it. Just looking at while, we were able to make the choice. Then after making that while, of course, there is nothing about this symbol, then I had to do, there is an expression, right. So, I come to the expression and here I have a term op term, and from the term, like when I came to the term, I had no doubt whether to use var name or constant, because the moment I looked at count, I know that I have to use var name. It is not that I used var name and then something went wrong, then I went and started using constant. So, there are at least in this whole scene, there are at least two cases in the case of statement and term where I have a choice whether when I land up with a statement, should I go for if or while or let. If I land up with a term, should I go and use a var name or constant, right. I have a choice here. And similarly, when I look at op, should I use plus, minus, equal to, less than, greater than. At any of these instances, I never need to I had no doubt of which rule should I use. For example, when I came to this term, I knew that I have to use var name and then count. I did not use term constant and then found count, and then just by looking at what is the next token, I can decide on what rule I should apply. Similarly, when I came to 100, right, I saw expression is a term. At this time, the moment I saw 100, which is my next token, I had no doubt of using this constant to 100 rather than this var name. So when I was looking at count, I used var name. While I was looking at 100, I started looking at the constant here, right. So at any point in this grammar, I never have a reason to actually go back. I can just look at the next token and decide which rule should I apply, right. So that is why. So I need not. So that is what we mean by this big statements that we have here. We'll go to the last bit. Yeah. So this is a grammar can be parsed by a recursive descent parser without backtracking. Backtracking means, oh, I made a wrong choice and go back, right. And this is called a recursive parser because these rules are recursive, right. For example, statement calls while statement. So statements calls while statement through statement. While statement again calls you statement. So the grammar is a recursive grammar, right. I can call myself in some way in this thing. So this is a recursive grammar, right. So that also we need to. So this parser is a LLK parser. What means? A parser that needs to look at most k tokens in order to determine which rule is applicable. In this case, this is a LL1 parser. I have to look at one token ahead to find out which rule I have to apply. So I look at this while and I know I have to do a while. The next is the thing, I need a symbol, I have to look at the current token. As of now, I have to look at the current token to basically find out which, I have to look at the current token to actually find out what is the rule I need to apply. Actually, as of now, as we had seen so far, I need not actually look at the next token. I have to just look at the current token to make the decision, right. Looking at this particular symbol, I know that this is a symbol. Just one token, the current token I have to look. So this is basically what we understand by parsing, and this is the output that we need to derive. Okay. So in the next module, we will now show you a little more larger implementation of this parsing, and we will show you how it becomes a LL1, why we need to look at one more token extras. Currently we are looking at the current token, we have to look at one more token extra. So why it becomes that, we will give you some examples as in the module 9.5. Thank you.